In this section, we will be looking at acid-base titrations. There are four main classes of titrations: acid-base, redox, precipitation, and complexometric or kilatometry. But today we will be looking at acid-base titrations. Titrations can be classified into various categories based on the type of analyte or the method of analysis. Based on the solvents used, acid-base titrations can be classified as titrations in aqueous solutions or non-aqueous solvents. As for the method, direct titrations or indirect titrations may be used. First, let's look at direct acid-base titrations in aqueous phase. One example of such a titration is between a strong acid and a strong base. Many indicators can be used, including phenolphthalein or methyl orange. Some examples would be in the assay of HCl, sulfuric acid, or thiamine hydrochloride. However, strong acid and strong base titrations are not very often used in pharmacopoeia assays. Can you guess why? It's because drugs are usually weak acids or weak bases. You seldom see strong acids or strong bases that are drugs. This graph shows the change in pH when a strong acid, such as HCl, is titrated with a strong base, such as NaOH. You can see that for strong acid, strong base titrations, there is a large change in pH at the equivalence point. Besides strong acid, strong base titrations, we can also do weak acid, strong base titrations or strong acid and weak base titrations. This is actually much more common because most drugs are weak acids or weak bases. Such titrations are used in the assay of benzoic acid and nicotinic acid tablets, which are weak acids, as well as chlorambucil injections, where chlorambucil is a weak base. Weak acids should be titrated using a strong base, such as sodium hydroxide, and weak bases should be titrated using a strong acid, such as HCl. Let's do some revision on what is a strong acid versus a weak acid. Strong or weak acids are defined by their ease of losing or donating a proton. For strong acids, when they are placed in water, they will almost fully ionize or dissociate straight away and produce H+ ions in the water. Whereas for weak acids, they will only partially dissociate and result in an equilibrium between the ionized and unionized form of that weak acid. However, one very important thing to note for titrations is that both strong acids and weak acids will be neutralized by the same amount of strong base. For example, 1 mole of HCl versus 1 mole of acetic acid, they will be neutralized by the same amount of strong base. It's just that their solutions will have different pH values. Similarly, the difference between a weak base and a strong base is the extent of ionization in solution. Strong bases are fully ionized in water, whereas weak bases will have an equilibrium between the ionized and unionized form. However, for titrations, it's important to remember that the reaction between a weak base and a strong acid will proceed to completion, meaning 1 mole of NaOH and 1 mole of ammonia, even though one is a strong base and one is a weak base, they will react with the same amount of strong acid. Let's take a look at the pH curve of a weak acid strong base titration. In this example, we have ethanoic acid, which is a weak acid, and it is titrated with sodium hydroxide, which is a strong base. The pH curve is shown in blue, and if you look at the equivalence point, the pH range at the equivalence point is actually smaller compared to that of a strong acid and strong base titration, which is shown by the black curve. Let's also take a look at the pH curve of a weak base strong acid titration. Here we have NH3, a weak base, which is titrated with HCl, a strong acid. The pH curve is represented in blue, And we can see that the pH change at equivalence point is also not as prominent compared to that of a strong acid, strong base titration, which is given in the black line. Now, how about a weak acid, weak base titration? Would we ever do a weak acid and weak base titration? Let's take a look at the pH curve. For example, ethanoic acid, which is a weak acid, is titrated with ammonia, which is a weak base. You will notice that on the graph, there is no steep beat or sudden pH change. Instead, we only have what is known as a point of inflection. So the lack of a steep beat means that it is difficult to do a titration of a weak acid against a weak base because the indicator will not show a sudden color change corresponding to the equivalence point. When discussing acids and bases, it is also important to realize that some acids or bases can donate more than one proton. This means that 1 mole of analyte is equivalent to more than 1 mole of titrant. If we look at the pH curve, you will see more than one inflection in the titration curve. So if you want to detect both endpoints, then you will need more than one indicator. Examples of diprotic acids or bases are sodium carbonate and oxalic acid. Let's take a look at sodium carbonate. 1 mole of sodium carbonate reacts with 2 moles of HCl to form 2 moles of NaCl, carbon dioxide, and H2O. If we take a look at the pH curve or titration curve, we can see two equivalence points, A and B. So for A, that is the equivalence point for the first part of the reaction, which is between sodium carbonate and 1 mole of HCl to form NaCl and NaHCO3, which is sodium bicarbonate. Then for stage B, sodium bicarbonate further reacts with another mole of HCl to form sodium chloride, carbon dioxide, and H2O. Let's take a look at another example, oxalic acid. Oxalic acid has 2 protons to donate, so in the reaction between oxalic acid and sodium hydroxide, you can also see 2 equivalence points. Besides the direct titrations that we are all very familiar with, another method for titrations is indirect titrations. This is also known as residual or back titrations. Indirect titrations take place in 2 steps. In the first step, a reagent is added in excess to the analyte, and the reagent will react with the analyte. In the second step, the amount of unreacted excess reagent is then determined through titration. Let's take a look at the diagram which illustrates how indirect titrations are done. So in the beaker on the left, this is the first step. In the first step, an exact volume of reagent B is added to the analyte A. This reagent B is added in excess, so there is remaining unreacted reagent B. In the second step, which is on the right, this remaining reactant B is then titrated with a titrant T. The amount of analyte A can then be determined from the difference between the added amount of reagent B and the remaining excess of reagent B. But why would we do indirect titrations, which seems to be more complicated? There could be several reasons why direct titration is not feasible. For example, the sample is not soluble in water. The sample contains impurities that could interfere with forward titration. The reaction could be too slow or side reactions may occur, so direct titration is not feasible. Or the endpoint of the back titration could be more easily identified compared to the forward titration. One application of indirect titration is in the assay of esters. Esters can hydrolyze to carboxylic acid and alcohol when they are reacted with sodium hydroxide. However, this is a very slow reaction, so it's not feasible to do a direct titration of esters with sodium hydroxide. So in the method of indirect titration, an excess of sodium hydroxide is added to the ester. Then it is allowed to stand for about 1 hour so that the reaction can take place. And at the end, the excess remaining sodium hydroxide is titrated using HCl and phenolphthalein as an indicator. This assay is used for the assay of different esters, for example, acetyl salicylic acid, cod liver oil, benzyl benzoate, and so on. Another application of indirect titration is in the assay of alcohols. Alcohols are difficult to determine using any other methods. So for the assay of alcohols, the alcohol is first reacted with acetic anhydride in excess. The excess remaining acetic anhydride is then titrated with sodium hydroxide using phenolphthalein as an indicator. This assay is used in the assay of benzyl alcohol, which is a preservative, as well as cetosterol alcohol, which is often used in creams. One more application of indirect titration is in the assay of insoluble salts. Because it's not soluble in water, it's difficult to determine the amount of insoluble salt using a direct titration. So it's more accurate to use back titration or indirect titration instead. An example is calcium carbonate, BP. BP stands for British Pharmacopoeia. This is used for indigestion. So to do the assay, a known excess volume of HCl is added to the calcium carbonate, and any unreacted excess HCl is back titrated with NaOH. So far we have been looking at titrations which take place in the aqueous phase. But there are also titrations that are performed using non-aqueous solvents, and this is commonly used in pharmacopoeia assays for drug substances. So why would we use non-aqueous titrations? It could be that the sample is insoluble in water, or it reacts with water in undesirable ways, and most commonly is actually used for the analysis of very weak acids and bases. And remember, many drugs are weak acids and bases. So why can't we do titration of very weak acids and bases in water? Water behaves as both a weak acid as well as a weak base because it can do self-ionization, and it will suppress the ionization of very weak acids and bases. In other words, water will compete with these weak acids and bases to donate or accept protons. For example, a weak base, RNH2, would react with a proton in an acid-base reaction to form RNH3+. At the same time, water, H2O, can also accept a proton to form H3O+, and this water will compete with RNH2 for that proton. So if we were to perform titration of weak bases and weak acids in water, the detection of the endpoint would be difficult, especially for bases with pKa less than 7 or acids with pKa more than 7. Just a quick reminder, pKa is a measure of acid strength. So the lower the pKa, the stronger the acid, and the higher the pKa of a base, the stronger the base. So here we are referring to very weak bases with pKa less than 7 or very weak acids with pKa more than 7. So in comparison with water, organic solvents would compete less with the analyte and allow for acid-base titration to take place. So how do we do non-aqueous titrations? For very weak bases would be dissolved in glacial acetic acid and it will be titrated using perchloric acid. Acetic anhydride will be added to the acetic acid to remove any water that's present in the solution. Acetic acid is a very weak proton acceptor and does not compete with weak bases for the protons, and that's why it can be used as the solvent for the titration. For the indicators, there are several indicators that can be used: orosette blue, quinolidine red, and crystal violet. Non-aqueous titrations are used in the assays for adrenaline, codeine, chlorhexidine, as well as metronidazole. For very weak acids, the solvent that is used is usually dimethylformamide or DMF, which also does not compete with the weak acid for proton donation. The solution is then titrated with tetrabutyl ammonium hydroxide or potassium methoxide. The indicator can be thymol blue or it can be potentiometric detection. And some examples are in the assay for sulfonamides, barbiturates, and phenytoin. Here are some points to take note of while doing non-aqueous titration. Firstly, all equipment and apparatus must be kept completely dry. Not just the solvents, but also the glassware. The glassware should be rinsed with distilled water and then with volatile solvent and then dried thoroughly before use. A second point to note is that temperature should be controlled. Titration in non-aqueous solvents is very dependent on temperature because organic solvents tend to expand more than water when heated. So it's important to measure the temperature when performing the titrations.